Danielle, and good afternoon to everyone that is watching this afternoon. Today, as Danielle mentioned, we'll talk about seismic acquisition. And for some eye candy, I have up here some vibrator trucks. It looks like 1, 2, 3, 4 of those. And then I have a marine seismic acquisition vessel. So we'll talk a little bit about land acquisition. We'll also talk about marine acquisition. I've added this terms of use. It is on the website. I'm not going to read all the words here, but the intent is that these materials, the lectures, the exercises, the videos are for full-time students and for teaching staff at universities. They are not intended to be used by people who are already working or any type of in-house training, whether that's done by a company for their own employees, or if it's a contractor coming in and doing teaching or training. So seismic image, we have to combine the seismic data acquisition and the seismic data processing. So today we'll focus on the acquisition part, and on Thursday of this week we'll talk about seismic processing. Acquisition and processing has to work together in order to produce the best possible final imaging. The acquisition process includes first generating a signal with an energy source, and we'll talk about the energy sources that we use, and then we have to detect and record the reflections that we have come back up to the surface, and we use receivers, and we'll talk about the types of receivers. Our ultimate goal is to create either a 2D line or series of 2D lines or a 3D volume of seismic data that adequately samples the geology that we're trying to map and interpret and make business decisions on. We want to optimize the data through signal enhancement and also through noise reduction. Some of the signal enhancement and noise reduction is accomplished in good data acquisition, and additional signal enhancement and noise reduction is accomplished through seismic data processing, which I'll talk about on Thursday. So keeping this goal of getting good images and worrying about costs, then we have to specify a series of acquisition parameters, some of which is the type of source and its source characteristics, the receivers and how far we space the sources and receivers. We need to worry about the surface area we need to acquire the data from, the record length, how many seconds of two-way travel time information are we going to gather, and then methods that we can use in acquisition to try to mitigate noise. The seismic signal is sampled at discrete time intervals, and we call that the sample interval or the sample rate. Jumping down to point 3, in the 1960s, prior to that, the industry was recording the wiggles as you would see on an earthquake seismograph. And then in the 60s, we started actually recording the data as digits. And so we have to have a certain sample rate. And so typically the sample rate in industry is 4 milliseconds, although there are cases where we might have seismic acquired at a 2 millisecond sampling rate or even a 1 millisecond. Depends on the velocity structure that we're trying to focus in on, and the depth and how much resolution we need to get out of the seismic. So going from analog to digital in the 60s revolutionized our ability to process the seismic data and do signal enhancements. So we produce the signal, we use an energy source at the surface, and that energy it propagates down through the subsurface, and we can think of that as the energy. Let's say we have dynamite. That's not too common of a source these days, but it is still used in certain cases. We have a stick of dynamite, it explodes, the energy goes down, hits an interface, and comes back up, and our receivers or listening devices catch those reflected waves. The red lines show how the energy spreads out spherically, and the black arrows are ray paths, so that energy from the explosion, the seismic shot, or the dynamite explosion will go out along the surface horizontally, but it will also go down, hit an interface, and part will record that. We need to capture the reflected energy at the surface, and we want to try to get rid of unwanted noise. The arrivals that come back to the receivers are recorded digitally, and so each shot is recorded in the field with equipment. We move the equipment along and repeat second shot, listen, third shot, listen, fourth shot, listen, and so on until we get the data coverage that we are interested in. We can attenuate noise by using arrays of sources and arrays of receivers. And so if we have several sources, and there's a lot of science in how we build these arrays and what their properties are, what we want to do is maximize the vertical downgoing energy, and we'd like to cancel out the horizontal energy through interference effects. Similarly, with the receivers, there's a lot of science that goes into how to design receiver arrays. And so we have 1, 2, 3, 4, 5, 6 receivers, but they're coupled to give me one response at the central location. Again, what we want to do is cancel out the horizontally propagating energy and focus or concentrate or enhance the vertical energy coming up as reflected energy from the subsurface. To enhance the signal, what we'll do is we'll sort the traces from multiple shots into receivers, and we do that sorting based on a common midpoint, CMP. So we have a shot here, energy goes down. Let's say we're interested where this little red circle is, interested in that little piece of the subsurface. The energy, reflected energy comes up and hits this receiver. Then we have this source send energy down, hits the same area, it comes up and is recorded in the second receiver. The third source is activated, energy goes down, hits where the red circle is, and is picked up by this receiver. So what we will do is we'll take our field record that is organized shot by shot by shot, and we'll resort the data so that we get common midpoints. A certain shot coupled with a certain receiver will get us information at a common midpoint or a CMP. The benefit of doing this and summing the common midpoint ray path, which is referred to as stacking, that allows us to reinforce the geological signal while diminishing through destructive interference, random noise, source-generated noise, unwanted multiples, and surface waves. Some of the things that are in our raw data set that we can correct for using proper acquisition methods. So let me talk about marine acquisition first. Here's a picture of a marine acquisition vessel. What we use in the marine environment for the source for the energy are air guns. That's the standard and when we are working in a marine environment. This shows a flotation device, and we have one air gun here, another air gun suspended here. This will be a few meters in depth in the water. You can see the cables that are coming out. Some of those are electrical cables. Some of those are for compressed air. We put compressed air in a chamber within each of the air guns. When the gun is fired, a piston is open, a hatch is open, a piston forces the air out rapidly. The venting air creates a bubble or a series of bubbles, and the water pressure will collapse those bubbles. And when the bubble collapses, that's what generates our acoustic energy or our pressure wave. So it's kind of like blowing up a balloon. Blowing it up doesn't give out a lot of energy, but if you pop it with a pin, you get a fairly large pop of acoustic energy. So here's a picture. Here's the vessel acquiring the seismic data. We typically use 2 or more source arrays. So this on the left is labeled source array 1 or A, I'm sorry, and then source array B. B has just fired. You start to see some of the bubbles. A has fired maybe 5 or 6 seconds previously. So the boat sails along at about a speed of 10 knots. A fires, B fires, A fires, B fires, A fires, B fires. And so we are able to position these source arrays such that we can get a lot of subsurface coverage. I'll show more diagrams to help illustrate that. In the marine environment, our receivers, our listening devices are hydrophones. We are detecting pressure waves. So we have an outer casing of metal, and inside that we have pressure sensors. There's holes in the metal so that the pressure can be sensed. We put these devices inside of tubes called streamers. We fill them with fluids, and they're close to being neutrally buoyant. So these silicon-filled flexible tubes will trail behind the acquisition boat, and these days those cables are on the order of 5, 6, 7 kilometers in length. So here we have a little cartoon. Here's my acquisition boat. Here's my source array, 3 purple air guns, and I have 1, 2, 3, 4, 5 receiver arrays. The energy is going to go down. We're going to be worried just about this interface between the yellow and the brown. And the point of reference that I'm interested in is marked with the red circle. And as I click through this animation, the boat's going to go along. The ray paths are going to change as the source position and the receiver position change. And I want to count how many times I get a reflection or a bounce point off of this little red circle. So here's time 2, time 3. I still don't have any bounce points, and so that's what this 0 corresponds to. Time 4, I have a first bounce point. The energy from the array goes down and comes up and is detected by the closest receiver, and then by the second receiver, then by the third, then by the fourth, and then by the fifth. So fold is a name that, or a term that we use in acquisition and processing for how many common source receiver pairs we have that illuminates a particular point in the subsurface. And so as I went through this little animation, the fold went from 0 all the way up to 5. And for this length of cable, only 5 receivers, 5 would be the maximum. Okay, and so in acquisition, we collect the shot records. In processing, what we look for are common depth points or common midpoints. And so with different shot locations, different receivers will have a reflection point or a bounce point at that little red circle. So we talk about the fold of the data that corresponds to how many different source receiver pairs would illuminate a particular point in the subsurface. This is an example of the shot record. This is the raw data that we get in a marine situation. Here is two-way travel time in milliseconds. So this would be 1 second two-way travel time. This would be a half. This is the receiver number, which is also equal to the distance behind the boat. We have oh, I thought there was some animations. The line coming down diagonally straight, that's the direct arrival through the water column. The slope of this line tells me what the water velocity is. If we see straight line segments at a steeper dip, those would be refractions. And reflections are the events, the blacks and the whites, that are curved slightly downward. They are hyperbolic in shape. And we understand the physical equations here. We can calculate what those hyperbola are, and based on the shape of the hyperbola, we can get the average velocity to a particular depth point. So here again is a photo with some overlay on top of it. So here's source array A, here's source array B, and this boat is pulling 1, 2, 3, 4, 5, 6, 7, 8 streamers. So those are those silicon-filled tubes that have the hydrophones in them, and they can be 4, 5, 6, 7, 8 kilometers in length. A lot of equipment to keep track of, to tow through the water and try to keep spaced in the way that we want them to be spaced. So again, a diagram. Here's my, this is looking from above. Here's my acquisition boat. Here's array, the blue array and the red array, and I have 1, 2, 3, 4 streamers. And so if I consider from this source into this receiver, the midpoint would be this blue dot. This source into this receiver would be this blue dot. This source into this receiver would be this blue dot. And so I can map out where I would have bounce points or reflection points when the blue gun fires. I can do the same thing with the red gun when it fires. And so if I count the numbers of lines of blues and red circles, I have 4 blue and 4 red. So in this situation, every time the boat sails in one direction, it's collecting 8 lines of subsurface data. The quick way to do that is take the number of sources, in this case 2, multiply it by the number of receiver lines or streamers, 4. 2 times 4 is 8. So I get 8 lines of subsurface data. We'll switch now to land acquisition. This is a vibrator truck. It can roll into a position. You use GPS so that we know exactly where the trucks are. We don't use a single truck. We use usually 4 or 5 that are working to generate an array. The main part of the equipment is on this metal plate. The truck rolls into place. Hydraulics push the plate down to the land surface, and then it continues to push so that it actually jacks the truck up and the wheels will not touch the ground. So the entire weight of this truck will be on that plate. And then we have equipment that will vibrate that truck either up and down to generate P waves or left to right, back and forth to generate shear waves. And we will sweep through different frequencies, whether we're generating P waves or shear waves. One option for land sources is to use dynamite. We have to drill shallow shot holes 5 to 30 meters deep. So that increases the expense of using dynamite because we have to have equipment to drill the holes. The depth of the hole is chosen based on where we would get best coupling between the explosion and the subsurface. It is expensive, it's labor intensive, and there are safety issues because there are people that are not geoscientists that would use dynamite for purposes other than collecting reflection seismic data. We use these in areas where we can't get the vibrator trucks in. And so that might be where we have gravel or sand and the vibrators don't get good coupling. It might be in mountainous terrains where we can't drive those 4 or 5 trucks, or it could be in areas that are swampy The water in the swamps doesn't allow us to couple to the land very well, or in dense jungles, again, where we can't get those trucks driven into. The most common, I would say probably 90 to 95% of land acquisition uses vibrasize, is to use these vibrator trucks, which I've talked about. The plate is lowered and we generate either P waves or S waves. The impact on the surface is very minor. It's much less expensive than dynamite. The vibrators sweep through a range of frequencies, and that sweep is later compressed into a compact seismic wavelet through a process called correlation. I know of an example where they use vibrator trucks at Dallas-Fort Worth Airport, and they had these trucks vibrating on the tarmac of the runways, and you can imagine that the airport wouldn't permit that if these trucks were going to rip up their runways and have to have the runway shut down for several days in order for them to repave it. The receivers for land are called geophones. They detect motion, and the older ones, which is shown here, would have a central magnet and wire wrapped around it, and as the magnet moves, as the land surface moves, that would induce a current in the wire that is wrapped around it, and so that electrical voltage is recorded as a signal, and so that is how we collected the land data up until maybe 10 or 15 years ago. Now we have other types of receivers for land. They're called MIMS, and they do not involve magnets and coils. So here's a little cartoon. Here's my vibrator truck. This is meant to represent the array of vibrator trucks. I have a couple of receivers to the left and 3 to the right. Here's the little red dot. This is the portion of the subsurface I want to keep track of. And so at this position, the vibrator sends energy down, it reflects and comes up and is recorded by geophone number 1, and then it's recorded by 2. So we have a fold of 2 at this point. And then it is recorded in geophone array number 3, 3-fold, 4-fold, 5-fold, 6-fold. So again, with the common midpoint gathering that we'll do during processing, we will build a data set in this example that would be 6-fold. This is an example of a land shot record. This is called split spread because the vibration, or the midpoint, I should say, is in the center. And then we have data that is to the right, and that could be north or east or northeast. And we have data to the left. This is where my animations are. We can have refractions that we capture, which would be straight lines. We can have brown roll and all the big excursions, the big sweeps of black and whites near the midpoint is ground roll. And the reflections are the hyperbolic events either to the left of the midpoint or to the right of the midpoint. Here's a picture, and if I can count the tires, there's 1 set, 2 sets, 3 sets, 4 sets. I don't know if there's a 5th truck back there, but it's either 4 or 5 vibrators that are going to vibrate the ground. In a map view, we are going to have the vibrators vibrate where the red X's are, and the geophones are located where the little green circles are located. And so we could vibrate at this point, and the red represents the midpoints. This would be for the southern line of receivers. This would be for the central line of receivers. This would be for the northern line of receivers. And as we move from this shot point to this shot point to this shot point to this shot point, you can see how we're starting to get patches of subsurface coverage. And if we did this for the entire survey, we can generate a three-dimensional volume of seismic data. There is some artifacts, some things that are not geologic that comes about because of the way we acquire the data. We will see amplitude artifacts that is typically oriented in the direction that the equipment was moving. This is more apparent in marine surveys than in land surveys. And so on the right, I have seismic line A to A prime. This kind of magenta reflector that has the dotted cyan line through it, that's the water bottom. If I were to ask the computer, show me the amplitude values for that water bottom reflection, the cyan horizon, this is what it would look like in map view. Line A to A prime is here, A to A prime. And what you see in here is lineations or striations or stripes that are oriented east-west. And that's because this is a marine survey and the boat sailed west to east, turned around, sailed east to west, turned around, went west to east, et cetera, et cetera. And so it takes some time in terms of depth or two-way time to heal up the fact that we don't have continuous sampling along the surface. We have individual points, shot points, that are typically on the order of 12.5 meters apart. Processing assumes that we have a consistent acquisition geometry. Artifacts will decrease in magnitude as we get deeper and deeper into the subsurface or deeper and deeper in terms of two-way travel time. There are ways that we can try to mitigate some of these artifacts. In acquisition, if there's an area where we didn't have enough shots, we can go back and do some infill shooting. We can do some pre-processing by flexing bins or by doing something called trace interpolation, trying to estimate what the data would have been if we collected it in locations where either it was poorly sampled or we had excessive noise. We can do several things in processing to try to help that. And then post-processing, we can do something like taking this amplitude map and doing some map filtering to try to smooth out some of the high frequency noise. That's a purely cosmetic process. That is not what I would call science-based solution to a problem. So in summary, land seismic, our source produces ground motion that reflects off subsurface interfaces and is recorded by geophones that detect ground movement. The typical source for ground motion is the fiber-sized trucks, although occasionally we still use dynamite in areas where vibra-size is not effective. In marine acquisition, we use compressed air and use the air gun or air gun arrays. The recording or the receiving devices are called hydrophones that are pressure detectors. There's a lot of efficiency in acquiring a marine 3D survey, and that's acquired by boats that tow more than one source array. Most of the time it's 2 or 3 source arrays, and they tow multiple streamers. Typically these days, I don't think you would find a seismic vessel with less than 8 cables, and there are some specialized acquisition vessels that can tow, I think, 20 or maybe 24 streamers is the maximum that is acquired these days. Okay, so that concludes my prepared remark. Again, there's a lot that we could say about seismic acquisition, but in a 35-minute presentation, I've tried to give you the main highlights. And before I turn it over to Dr. Sumi, I'll just put this up. This keeps track of where we are. We've just finished seismic acquisition lesson 16. Thursday, we'll talk about seismic processing. So Dr. Sumi, I'll turn it back over to you if there are some questions from the audience.
Great, thank you. The first is, what is the seismic energy output comparison between fibrosice and dynamite?
What is the seismic energy? And then I heard vibrosize and dynamite, but I didn't hear the middle.
What is the seismic energy output comparison between fibrosice and dynamite?
The main difference is that dynamite produces a single pulse of energy with various frequencies in it, kind of like you would think of as an explosion or an earthquake. The vibrosize, we are shaking the earth, and we shake that at different frequencies. The vibrators will sweep either high to low frequency or low to high. And so it's not a single event, it's a series of shaking with different frequencies. And that's why we have to do the step that I mentioned, correlation, to get that back to replicate what it would have looked like if it was a single impulse like an explosion.
Great, thank you. That was our first and only question so far. I seen, okay, here we go. Dominic asks, the geophone offset / spacing is 12 meters, as you said. Sorry, the English is a little weird. This supposed to me, that's not right, but that we cannot see any structures less than 12 meters in radius or small than the line spacing.
Yes, okay. First of all, typically the receiver spacing will be 25 meters, and then when you consider the fact that the energy is going down, bouncing, and coming up at a reflection angle, that cuts it in half, so it's 12.5 meter trace spacing. And I'm trying to remember what the other point that I was going to make. Oh, that does limit both our vertical resolution and our lateral resolution. We'll talk Thursday about seismic migration. Seismic migration greatly enhances lateral resolution. And so typically with today's seismic at the depths that we're typically interested in, our lateral resolution can be on the order of about 25 meters. And if we're in an exploration mode, we certainly can live with 25-meter lateral separation. Even if we're in field development or field production, we may want to understand where a particular fault is positioned in the subsurface. And if we have a lateral resolution on the order of about 20 meters or so, that is usually more than adequate in order to answer the business questions. So there are limitations, but in terms of the scale of things that we're looking at, it usually isn't too much of a handicap.
Great. Joanne asks, I have heard mention of using parasound in the marine environment. How does that compare to the type of marine acquisition you were describing?
Was that paracells?
Parasound.
Can you type that in for me?
Sure.
It's not a term that I think I'm familiar with. Parasound. Okay. I do not know what that is, so rather than guess and be totally off base, I'll just say you've stumped the presenter. Are we still connected?
Sorry, I was on mute. So
Okay.
Joanne says, okay, sorry, that's fine. Carlos asks, how to do seismic acquisition on high topography terrain.
On high topography terrain, I would say mountainous regions, that is where oftentimes we have to rely on dynamite. Again, if we can't get vibrator trucks to give us the necessary surface coverage, then the fallback is to use something like dynamite. In some cases, if it's a mountainous terrain, but there are a series of roads, they will use modeling of seismic acquisition to see what sort of coverage they could acquire if they just had the vibrator trucks vibrate on the roads and the logging paths and any place where they can get those fairly heavy, fairly wide vehicles into position.
Great. John asks, how are ground rolls extracted from the seismic data without loss of relevant reflection data?
Yeah, I think I'll talk a little bit about that on Thursday. But what we do is we try to figure out how can we isolate an unwanted effect such as ground roll or multiples, and then subtract that from the basic data and hopefully have a less noisy data set to work with. And so a lot of times we'll do a Fourier transform, and we'll take things from the two-way time domain into the frequency domain, and we can design filters in the frequency domain that will take out things such as ground roll and multiples. And so there's a lot of work that has been done in the past to try to eliminate different types of noise. And it's still an area of very active research. How can we minimize the noise, enhance the signal, and when we do subtract something such as ground roll, how can we try to safeguard that the data that remains is trustworthy?
Great. Fernando asks, do you expect seismic acquisition projects in the near future, especially considering the recent oil and gas downturn?
Yes, I believe acquisition will continue. I think it has continued. It is probably not at the same amount of work, say, per month as it has been in the past. And a lot of times what that means is the companies that specialize in seismic acquisition have cut their costs. So in the really good times in terms of high oil and gas prices, acquisition costs can go up quite a bit, and you may have to wait up to 12 to 24 months in order to get a slot so that the companies that acquire the seismic get around to doing your particular project. In the downturn, such as we've been in for almost 2.5 years, the price goes down, and also your wait time goes down, maybe to almost a couple of weeks. And so right now, all of the seismic acquisition companies have downsized quite a bit. They are still trying to get work for their people, for their company. Companies are still looking at new areas. They are still requiring new seismic data. Companies that have fields that are on production, they are still acquiring seismic data at a higher density, a higher data quality, so that they can make the right business decisions on how to manage the field. So as the price of oil drops and you're in a oil and gas production phase, you have to try to save money as well. And it may sound counterintuitive, but it may be beneficial to spend a few $1,000,000 on acquiring better seismic data so that you can position your wells better. The other area that acquisition is quite active is in our resource plays or our unconventional plays. So places like the Williston Basin and the basins in West Texas, where there's a lot of unconventional oil and gas drilling going on. I believe that the seismic acquisition activity is pretty high in those areas.
Great. Norman asks, do air guns produce enough energy to go through the whole water depth and reach to the seafloor with high energy, or weak signals reach to the seafloor?
Oh, with the air guns, we are able to get energy down to 40 to 50,000 feet. So we don't have trouble generating enough energy to get down to and even beyond the zone of interest that we're interested in.
Great. So that's all the questions that people wrote in. Thank you for this exciting Q&A session, Fred. And we look forward to Thursday on seismic processing. So thank you, everyone.
Okay, thanks everyone for your interest and for your questions, and I'll talk to you again on Thursday.
Sounds great. All right. Bye, everyone.
Hey, goodbye.